Good afternoon. The topic of my presentation is smart materials. As we know, since long, human has harnessed diverse materials to enhance their quality of life. The progress of the material technology has been remarkable, evolving from the primitive Stone Age to the current sophisticated era. Human interaction with the material stretches back to the prehistoric time. The Stone Age harnessed a variety of rocks, flint, obsidian, etc. to craft weapons and other tools. Furthermore, used natural materials like wood, bones, and animals' hides for different purposes. The subsequent Bronze Age was characterized by the extensive adoption of bronze like copper and tin. The superior hardness and the longevity of the bronze tools and weaponries compared to their Stone Age predecessor brought about transformative changes in farming practices and craftsmanship. In the 10th century, Damascus steel emerged as a pioneer material renowned for its superior strength and distinct pattern. From the 10th century Damascus steel to the 21st century's graphene, our mystery, our materials has continually evolved. The 13th century brought eyeglasses, while the 17th century introduced rubber, cast iron, generally produced in the century of 18th, followed by the steel and the aluminium in the 19th century. The 20th century witnessed a surge in the material innovation, including plastic and semiconductors. This period also saw the birth of smart materials, capable of responding to the environmental stimuli. These intelligence materials can alter their properties by offering certain distinct properties. The modern material science classifies substance under metals, ceramic, polymers, and other smart materials. The latter group stands out of the ability to change the shape and size under the external influences. Some even exhibit self-healing or the self-destruction property, surpassing the traditional material in functionality. The smart materials are classified into two main categories, like active and the passive material. Active materials possess the remarkable ability to convert energy from one form to the another form while remaining shielding from the external environmental factors. The active smart materials includes piezoelectric materials, shape memory alloys, magnostrictive materials, and electroactive polymers, etc. The active materials boost several advantages, including rapid response time, autonomous activation, and significant sensitivity to external stimuli. These properties enable them to readily alter their dimensions and configuration, granting them self-diagnostic capabilities. These self-diagnostic traits allow them to identify surface imperfection and autonomously repair them, a phenomenon known as self-healing. However, passive smart materials encompasses examples such as fiber optics, hydrogels, and self-cleaning surfaces. Furthermore, passive materials are limited to energy transformation, or we can say that modification without their protective features. Recent decades have witnessed the emergence of multifunctions material, or we can say the emergence of the multifunctional material, with researchers employing various analytical methods to investigate their properties. The field of material science has been a significant show the progress from the composite material to the shape memory alloys. These advanced materials have outperformed the traditional substance in many aspects. The synthesis of these intelligent materials now rely on the contemporary techniques departing from the conventional machining methods. In the era of Industry 4.0, smart materials or intelligent material, or we can say that the responsive materials, have garnered considerable interest owing to the distinct and superior thermomechanical attributes. Furthermore, we can say that the smart material have the capability of changing their form and regain its shape under external stimuli, along with the sensing and the actuation capability instead of conventional functionalities. These exclusive alloys were first discovered in 1932 by the Swedish scientist Arne Oleander. Meanwhile, it has been observed that the thermoelastic martensitic behavior also found in the gold and the cadmium alloys. Furthermore, searching for the novel alloys and their manufacturing techniques was carried out The tremendous progress in the academic and the industrial purposes, or we can say the industrial perspective, has significantly enhanced the comprehension of such stimulus responsive material in the recent past. Among several smart materials, shape memory materials like shape memory alloys, shape memory polymers, shape memory ceramics and gels, etc., possess unique properties and the characteristics. Furthermore, novelty of stimulus response material includes self-healing, shape memory, electromagnetic active phenomena. So the shape memory alloys, if we are talking specific to the shape memory alloys, and these alloys are the distinct category of the smart materials that have capability to recover its memory after being deformed under several loading conditions. This loading conditions are either in the form of a temperature, pressure, or certain amount of load. The shape memory alloys can be classified into in the form of copper based, iron or nickel based, or we can say silicon, titanium, or any combinations we can say. So there are several types of shape memory alloys are available depending upon the composition of the material that we have chosen. However, these shape memory alloys has inherent limitations and drawbacks. Thus, among several, nickel and the titanium is the one of the most preferred one in the shape memory alloys, as nickel titanium based shape memory alloys are the exclusive category of the shape memory alloys capable of changing their structure, compositions, and different either in the mechanical or the electrical property under the influence of various environmental stimuli like temperature, stress, pressure, magnetic, and the electric field. These alloys exhibit a unique characteristics of retaining their initial configuration and when subjected to applied load or pressure, or we can say deformation. However, they revert to their original shape through the suitable process of heating and the cooling. The first such type of nickel titanium based shape memory alloys has been generally known as a nitinol, was first discovered by W. H. Buehler in 1963 at the United States Naval Ordnance Laboratory. It has two distinct properties like super elasticity and the shape memory effect. So if you talk about the shape memory effect, it was initially identified in 1932, and until 1971, it has been assumed to be a common to all alloys underwent thermoelastic martensitic transformation. Furthermore, nickel titanium based shape memory alloy have unique properties including high actuation stress, recoverable strain, mechanical strength, biocompatibility, and corrosion, wear resistance, etc. So this type of alloy are loaded and thermally actuated. It exhibit the distinct features of shape memory effect due to the reversible diffusion martensitic transformations. The parent denotes as there are different phases in the materials. The parent phase is known as austenite in the case of if we are talking about the nickel and the titanium based shape memory alloys. So different phases has been there either in the form we can say high temperature phase or we can say a low temperature phase. So there are two phases either in the form of austenite or in the form of martensite. Intermediate state has been also there. We can say the intermediate stage featuring a rhombohedral distortion discernible between the parent and the product phase in terms of R phase. Within the specified limits for the applied load and the temperature, nickel titanium shape memory alloys can undergo 6 possible transformation under different conditions. The transition from austenite to detwined martensite during the cooling or the loading process, the reverse is also possible, and we can say several other deformation has been there. So if we conclude this about the smart materials, so in this state, in this current era, or we can say in the industrial 4.0, we have seen that the tremendous use of this material either in the form of biomedical application or in the form of aerospace, etc., etc. So continuously we are evolving and searching for such type of material that will help for the human development and for the welfare of the human being. So this is all about the basic idea about the smart materials. Thank you.